after the workshops and the coffee break. It is my pleasure to introduce our next guest, which is Professor Anatoly Polkovnikov. He has quite an impressive academic history. He has done his PhD at the Yale University, followed by a postdoc at the Harvard University. And finally, he settled at the Boston University at the physics department, where he has been working for a total of 16 years. His research interests are mostly centered around widely understood condensed matter physics, and his papers were published in various reputable journals, and they gathered in total over 14,000 citations, which directly shows the impact of our guest on physics and science in general. Today, he will give a presentation on engineering approximate counter-adiabatic protocols in complex systems. He also encouraged the viewers to ask questions during the presentation. It is an honor to have you here. Thank you for coming, and the floor is yours.
Okay. Well, thank you very much for inviting me. So let me start sharing. Right, so I will tell about engineering actually there is a type, it should be counter-adiabatic protocols. Anyway, in complex systems. This talk is based on a series of works I was involved in with many people, former students, postdocs, former postdocs. I want maybe emphasize Dries Sells, who is now a professor at NYU, with whom we sort of started this business, and also maybe Peter Kleiss, who is now in Cambridge, who actually did some important contributions, but all other students, former students, they contributed. So indeed, I will strongly encourage asking questions. And before I start, let me maybe just tell a little bit about logistics. So because this is a lecture, not just a talk, I thought I will include some technical parts, at least some basic equations. I know usually it's hard to follow during the talk. So my idea that if some of you are really interested in these topics, you will kind of have to repeat it and try to reproduce some of the calculations. So maybe open the relevant papers, just send me an email, I will send you references and so on. If you are less interested, you just want to know, then basically skip, just don't listen to me when I explain equations, and then just listen for the results. All right, so let's start. Please ask questions, and let's see how it goes. So I will be talking mostly about quantum systems, but there is an interesting psychology that very often people think that quantum systems are more interesting and so on than classical. But many of the recent results people are working on, including, you heard lectures from Marcus Riegel on thermalization, generalized Gibbs ensemble, like ergodicity breaking and so on, they equally apply to classical systems. So I thought I will mix the language of classical and quantum a little bit before going to quantum examples. So I will start from classical systems, and then I will sort of explain how I can translate this language to quantum systems. And in some sense, classical systems are more intuitive, so there is also advantage in doing so. So let's imagine first the simplest problem where we can formulate all these ideas of counter-adiabatic driving and so on. Let's imagine that we have, say, a particle in a box, and by box I mean some potential V, which depends on some parameter x naught. So here, this parameter is like center of mass, say, position of the box. But you can imagine this parameter could be, say, width of the box, or maybe if it's a spring constant, you can just change stiffness or whatever. It could be magnetic field or whatever. But just for simplicity, let's focus on this particular parameter. And then suppose we want to solve dynamical problems. Say, assume we have particle inside, either it's in some quantum stationary state or it's in microcanonical ensemble. which is equivalent classically. And then we want to move this potential. And then we want to understand what particle is doing. And actually, it's a pretty hard problem because we need to solve problem with time-dependent potential, time-dependent boundary conditions. We don't really know how to do it usually. But here we can sort of do a trick. We can realize, well, let's go to a moving frame, right? So it's like if you are sitting on a train and playing some game like with a ball or whatever, we prefer to solve the problem, like understand what ball is doing in the moving frame. So let's do the same. So once we do this, our Hamiltonian becomes extremely simple because this is a canonical transformation which we don't touch momentum, but we translate coordinate. So momentum remains the same. Now this combination becomes psi, which is just time-independent coordinate, right? It can still change in time if I have a motion of this particle, but at least this coordinate doesn't change in time. Definition of coordinate doesn't change in time. And potential is static, therefore. And then we get an extra term, right? Yeah, I assume you're all familiar with it. It's Galilean transformation. We get minus Vp. So now let's see what happens. So we have now a problem with fixed boundary conditions, but we have an extra time-dependent term, right? So this last term is actually is responsible for all non-adiabatic effects. So you can imagine that again, quantum mechanically, the particle, if you start accelerating the box, the particle will start jumping between energy levels, right? It will say we start from a ground state and then it will end up in another state. So classically, if you start in microcanonical ensemble, we'll end up in a broad ensemble, right? If you start accelerating, some particles will collide with this wall, some will not, and then we get some broad energy distribution. Everything comes from this term because this is the only term which is time dependent, right? Even if you move with constant velocity, I just want to emphasize we need to accelerate at some point, right? So this term has to be time dependent for any dynamics. So, and the idea was actually amazingly simple. It's quite recent. It, I think, was formulated first in 2003 by Dimmer, Plak, and Weiss. And the idea is that, well, let's just drive the system with counter-diabatic Hamiltonian, which is original Hamiltonian plus this term, right? And of course, for Galilean transformations, this idea is very old. I mean, Greeks knew about it and so on. Everyone knew about it. But general formulation, I think, is quite recent. Then let's see what happens. In the moving frame, when we go to the moving frame, we need to do this Galilean transformation. And we do it, we kind of undo this term. And then in the moving frame, our Hamiltonian is completely static. So it means that whatever we do, nothing happens to our particle or our ensemble, right? So the moving Hamiltonian is static for any dependence x0 of t. And by the way, from this, you can also see how adiabatic theorem works. So if we don't do anything, just move slowly, this term is small. And you all know that if we move slowly, we have adiabatic theorem. So this term is negligible. So it's probably the easiest way to see this adiabatic theorem again in classical quantum systems. Okay, so there is one subtlety, and this is how we implement this term. And actually, I will come to that later in the second part of my talk, or towards the end of the talk. But here it's relatively simple. Like the term is v times p, right? V is velocity of the box. So, but what do we do with this term, right? Well, if you have charged particle, you might recognize this is exactly a vector potential, right? Because I can complete the sphere square, and then I just shift the momentum. That's exactly what vector potential is doing. So we can apply, some electric field which has exactly the same vector potential and so on. But what if particle is neutral? What do we do? Well, from electromagnetism, we know that there is a gauge equivalence, right? So we can trade in between time-dependent vector potential and time-dependent scalar potential. Remember, we just add gradient of the function to the momentum and subtract derivative from the Hamiltonian. So this is like a trick. And then if you do this exercise, you'll see that this Hamiltonian is equivalent to this, right? So, and this is something very familiar. So what I'm saying is that if you want to realize this counter-diabatic driving, what you have to do is to apply gravitational field, which is opposite to acceleration. And you, of course, know, because if you start moving in a train, there is inertia force. This force, I don't know, makes all non-adiabatic transitions, right? If you put a glass of water and train starts moving suddenly, grass will fall down. So that's exactly a non-adiabatic effect. But if you apply gravitational force which counters this acceleration, nothing will happen to the glass. It will not move. So there is a subtlety, though, that usually we know that gauge transformations are harmless. It's a little bit untrue. So it's harmless when you do equilibrium, but when you're doing non-equilibrium, you're sort of changing your, I don't know, canonical variables. So what you have to do in addition is to require that initially and finally velocity is zero, because then you're making sure that initially and finally your transformed momentum, shifted momentum is the same as original momentum. So I'll come back to quantum systems shortly, but basically it's sort of easy to see, or at least I will explain what I'm doing here in the quantum language. I'm just saying I'm finding another unitary transformation such that it's identity in the beginning, in the end, and I'm driving with the Hamiltonian, which is unitary transformed. So, and then I can guarantee that my wave function will follow not the ground state or whatever, any excited state of the Hamiltonian. That's what counter-diabatic doing, but does extra unitary rotation. But if it's unitary is identity in the beginning, in the end, in the beginning, in the end, I basically start from the same function I prepared and end in the function I want. This is a subtlety, maybe I'm too fast, but this is something to keep in mind, because in the lab, usually it's much easier to implement this protocol. I mean, of course, when we do it implementation experimentally, we don't think about, I know, this unitary transformations and so on, but this is effectively what we are realizing in the lab, this unitarily transformed counter-diabatic Hamiltonian. So, well, this is like a small cartoon. Actually, we came up with this, I think, this example with a waiter just to illustrate what goes on and to highlight that this simple example generalizes to more complex systems. So if we don't do counter term and we move fast, we have a lot of non-adiabatic effects. And if you apply counter term, then we can suppress excitations, at least to a large degree. We have to realize that this glass with water is extremely complex systems, right? And then we can imagine that if we tilt that way, at least we will be much more adiabatic. So another example, which I guess is also familiar to you. So let's imagine we have a rotating frame. So suppose we go to this merry-go-round, which rotates, and want to understand, say, how the ball jumps. So we throw the ball from this horse and study its motion. Again, we can do it in the lab frame, but it's very complicated because we have to take into account that boundary conditions change when ball touches and so on and so forth.
I'm sorry, Professor.
Yeah.
A question emerged, I think, concerning the previous slide. Yeah. Alexander asked, or even the previous one, what does the D term stand for in HFF?
D? Where is D? Sorry, I don't see D. Oh, FF? Sorry, what can you repeat?
Yeah.
Oh, it's called fast forward. I forgot. Yeah, people use, sorry, that's a good question. I forgot to tell. So people generally frame like various approaches as shortcuts to adiabaticity, STA, right? And there are various sort of sub names for different things. So counter-diabatic is literally this, where you really follow ground state of the same Hamiltonian. Fast forward is usually understood in a broader sense that you don't follow instantaneously ground state of instantaneous Hamiltonian. Like, for example, here, clearly ground state of instantaneous Hamiltonian would be particle not moving, but if you apply this Hamiltonian, particle is moving with a box, right? So you're not following ground state of instantaneous Hamiltonian, but you follow it in the beginning when box doesn't move, and in the end when box also doesn't move, right? So, and people call it fast forward. I think maybe later names will saturate to some single name. I guess STA now is the name which takes over. And usually names appear when people come to sort of the same or almost the same formula from different angles. So fast forward protocols was developed in I think in MR, I forgot. And originally it was not even related to count adiabatic. So people just asked, can I generate Hamiltonian by adding extra term that I will end up in the same sort of state?
I think it also concerned the quantum language and the term D with lowercase t.
Lowercase
t.
Yeah, I will explain it. If you do this time-dependent transformation and put into Schrödinger equation, you'll have to differentiate both unitary and this. I will explain it in a second. This is precisely this Galilean term. Okay. So this is exactly the term which appears in the moving frame. Yeah, I wanted to go a little bit out of the order here because sort of in quantum language, it's probably more natural to understand what we are doing. But yeah, I'll come to that. So just bear with me for 5 more minutes. So yeah, so rotating frame. So we know again that if we go to a moving frame, so we define new set of coordinates which change together with this merry-go-round, which rotate, right? So my new coordinate depends on theta, which depends on t. And this coordinate can still change in time, right? So I define time-dependent definition of coordinate if you want, and ask how it changes in time if I don't know, throw the ball, right? And you also all know from mechanics that I will get an extra term, which is angular velocity times angular momentum, right? And then my counter-adiabatic Hamiltonian will be, I will need to add this term back. So basically, if you want, this is also done for spins, that I create like artificial magnetic field. If I have a spin, this magnetic field will couple to dipole moment, which is proportional to angular momentum, right? And then I can compensate for rotation. So, but this is an example where this fast forward protocol is not easy to realize because, if you have magnetic field, there is no simple gauge transformation which removes it. It just doesn't exist. So here it looks like if we want to go to rotating frame, we have to find a way to implement this guy. Okay. So now, what is the general approach? I just gave you examples, and maybe that's all to it. So what I'm talking about? Well, let's try to generalize our thinking. So what we are doing really, we are trying to find a canonical transformation where the Hamiltonian looks time independent, right? So we will generate additional terms, but first we want to make Hamiltonian time independent. So that's what we were doing with the car. That's what we're doing with rotations. So now what are the canonical transformations? Well, these are those which preserve Poisson brackets, right? And then this is something which probably you didn't see, but you'll immediately recognize. So if you say that there is arbitrary function, I call it A lambda, which is function of x and p. And if you define infinitesimal change of coordinates in this way, so dx by d lambda, lambda is some parameter. It could be like your angle or position or magnetic field or whatever. So if you define that dx d lambda is the same as minus dA dp, and dp d lambda is dA dx, then it's very easy to check that Poisson brackets are preserved. So this guarantees that this is a canonical transformation. And moreover, any continuous canonical transformation can be written in this way. So if you learned about generating functions, so this A is related to generating function. So now let's see what the equations of motion are. So now, see, we have x, which depends on lambda. So this is how we define x of lambda. But lambda itself can depend on t, right? So, and then when we go to a moving frame, so like to our rotating frame, and right, what is dx dt? Well, it's dx dt at fixed lambda plus dx d lambda times lambda dot, right? But dx d lambda is equal to minus d lambda dp. So here, well, basically what you see is that you recover Hamiltonian equations of motion with a moving Hamiltonian h minus lambda dot a. Okay, so this is general, but now we can ask which transformation makes Hamiltonian time independent. So in quantum language, which transformation diagonalizes Hamiltonian? Well, it's the one where new Hamiltonian after transformation, we change parameter lambda, in new coordinate is like a conserved quantity. So in quantum language, it means its commutator with original h is 0. In classical language, it means Poisson bracket is 0, right? So you see, if we change just Hamiltonian without changing coordinates, we induce dynamics. So in quantum language, it will not commute with original Hamiltonian. But now we are trying to find how we change the variables such that this Hamiltonian basically commutes. Before we were requiring more, we were requiring condition that Hamiltonian looks the same, right? So remember, with the moving frame, after our canonical transformation, Hamiltonian was exactly the same at all moments of time, right? So it's p squared over 2m plus v of psi. It turns out this is a little bit too much, so generally you cannot really satisfy that. But you can have a weaker condition that it commutes. So for example, Hamiltonian can stretch, right, by some factor or do something else. Okay, so now we just say what derivative of Hamiltonian is. It's partial derivative plus derivative because we are changing coordinates. And it's very easy to see that this is nothing that Poisson bracket with our A, which is adiabatic gauge potential. So basically, long story short, and this is, I'm sure if you never saw it, I was too fast, but this is something you can return. Basically, this canonical transformation we are looking for should solve this equation. So we look into change of coordinate, then add extra change due to change of canonical variables and require that this has a vanishing Poisson bracket with original Hamiltonian. And if we can solve this equation, we can do many, many things, really. We can implement this counter-adiabatic driving, and we can solve all our energy problems, right? We eliminate dissipation, we can build quantum computers, and so on and so forth. And there is one caveat, which was actually realized in 1995 by Chris Jarzynski as in first one. So that actually this equation in chaotic systems doesn't have a solution. It's very simple looking equation. It's like Poisson bracket, like double Poisson bracket, we just write it. And if we, try translations, you can do this exercise, you will find that A is momentum. So momentum generates translations in quantum classical systems. If your lambda is an angle, you rotate and then you see, well, you'll get angular momentum. So again, there is a solution. But if you try to have like, some system without symmetries, you can take two-dimensional billiard or some other system and try to solve the same equation for lambda being anything like extra shape, extra strength of something. Then you'll generically find that we just cannot solve it. So this is the problem. Now let me go finally to the quantum systems. So what we do there, well, we, instead of going to time-dependent coordinates, we are going to time-dependent basis, or in some sense, equivalently, we can say we are doing a unitary transformation on psi, and this unitary instantaneously diagonalizes Hamiltonian, right? But because our parameter depends on time, this is a time-dependent unitary. Then we substitute this into Schrodinger equation, and then it's very easy to see that we get extra term, which I was discussing before. I said it's IH bar d by dt, whatever you dagger, but here I just use a chain rule, and I say, because U only depends on lambda, so I just say it's lambda dot times d by d lambda. So this is extra term which comes because I have to differentiate unitary. Just do this exercise, you'll see where it comes from. So anyway, so what we see is that exactly same form. So moving Hamiltonian gets extra lambda dot a lambda, and we just compare with classical system and see that it's the same object. So counter-adiabatic driving will be when we add this term back, right? And then in the moving frame, our Hamiltonian, tildes, forget about it. It's which basis you work, so ignore tildes. So this is basically a moving Hamiltonian. So in this moving Hamiltonian, if you want, you write your equation in time-dependent basis, but you ignore the fact that time basis depends on time. So instead, you get extra term in the Hamiltonian, and time derivative only acts on components of wave function on this basis. That's what we are doing. This is trade-off. So, and then if you apply HCD, count adiabatic, then in the moving frame, this term will cancel this term, and our Hamiltonian will be again original Hamiltonian. And then you get exactly the same equation. You just ask, well, which transformation diagonalizes Hamiltonian? Well, it's basically we have Hamiltonian in its own basis diagonal, and we introduce change in the Hamiltonian, and then we additionally do unitary rotation, and we require that new addition of the Hamiltonian still commutes with the original Hamiltonian. So we're getting exactly the same equation. So, and of course, the same issue, but now a situation is a bit easier. If we deal with finite dimensional matrices, this equation always has a solution. Moreover, it has degenerate solutions. So the problems comes if we take thermodynamic limit or classical limit in chaotic systems. Okay. So how do we find this adiabatic gauge potential? Well, I said there is exact solution, and indeed quantum mechanically, this adiabatic gauge potential is basically derivative operator. It just tells us how eigenstates change. Well, if you say n of lambda is some u unitary times n naught, and use the definition which I wrote, you will exactly get so. And then you can again see it's sort of like a momentum operator, angular momentum operator. So, and this we know how to solve, right? We just use first order perturbation theory. We just ask how eigenstate change if we change parameter lambda infinitesimally. And we know that matrix elements, we just take ket m, and then we ask what's the overlap of these guys. And we know we get in numerator your perturbation, which is change of Hamiltonian, in denominator, you get energy difference. So this is just first order perturbation. And you can immediately see it solves this equation. Maybe I'll skip it, but if you multiply by n minus em, you'll see that it works. So, but this is difficult, and as I said, even impossible. But what one can show, and for this I don't have time to explain, but it's also easy, that this equation is actually equivalent to minimization problem. So we just take this object, I take a g, so it's basically d lambda, my change in the Hamiltonian plus contribution from rotation, take square of it, take trace, and minimize over all possible a of lambda. And it turns out that minimum is precisely the correct result. Well, in minimization problems already a step forward, because we know if we minimize something, we can try to find approximate solution, right? That's how all variational principles work. And this is not exception. Okay, before going into that, let me actually spend some time on relation of this adiabatic transformations and chaos. Originally, I was not planning to talk about it, but I realized that Marcus Rigol, with whom we're collaborating a lot now, gave you a talk about ETH and so on. And I thought it's sort of nice to connect this thing. So I'll spend maybe 5 slides on talking about something else. So, it turns out that this generator of adiabatic transformations, and this is actually what we are finding it when we do our first course in quantum mechanics and do non-degenerate perturbation theory. We are secretly finding this operator. No one tells you about this, but that's what we are doing. So it's an object which is extremely familiar, right? And you see that this is exactly, as I said, expression which appears in first order perturbation theory. This is your first order coefficient of n state in the basis, in the m's basis of unperturbed Hamiltonian. But now let me play a little bit and try to connect it to dynamics. So, right, so this generator of adiabatic transformations, but it turns out it's also related to long time averages of various objects. So you can probably bear with me, and you can see that this energy denominator I can get by its sort of time integral, right? So if I take this integral and well, evaluate exponent, epsilon is an infinitesimal number, I will exactly get this. Again, yeah, there is what h bar missing, but doesn't matter, right? And now I can put this En minus Em under this Hamiltonian and realize this is d lambda h in Heisenberg representation. So to make long story short, it's actually this A lambda. It's easy actually to write it as asymmetric integral to get principal value. But anyway, this is a detail. So instead of from 0 to infinity, I integrate from minus infinity to infinity, but then I need sine t. So this A lambda is nothing but this asymmetric integral of my d lambda h in Heisenberg representation. So classically, it's just how d lambda h depends on t. So it's d lambda h is my perturbation. So I plug in my x of t and p of t. This is my classical function, which is analog of this operating Heisenberg representation. And then I take infinite time integral. I regularize it with epsilon, which I sent to 0 at the end. I won't write limits anymore. It's my small parameter. And then I can ask, what is G lambda? Remember, this is an object which has to commute with Hamiltonian, and it's equal by this to this expression. Well, it's nothing but actually time average of d lambda h in the Heisenberg representation. And it turns out that these are, these are conserved quantities. If you take any operator and time average it, only diagonal elements will remain. And these are integrals of motion. And I think at least the first work I know when these integrals were introduced and used is in work by Marcin Mirzewski, Peter Prilovchik, and Tomasz Prezen. And they used it to find some missing integrals of motion for generalized Gibbs ensemble. It's very efficient numerically. And then it was used by many groups. So, and there is this interesting connection, which I personally don't understand quite completely, that when we are asking which object generates adiabatic transformations if we do small change in our parameter lambda in the Hamiltonian, we are actually also asking a question about like conserved quantities of the corresponding conjugate to lambda, d lambda h, at fixed Hamiltonian, right? So nothing changes in time. So here d lambda h is just conjugate to h. If my lambda is magnetic field, this is magnetization. If it's electric field, it's dipole moment. So it's just the way to write generalized force. So this is some local operator. Then we look into Heisenberg representation, time averaged it, and then we get G, which is related to this A. So adiabatic transformations actually know about dynamics, and moreover, they know about long time dynamics, right? Because I need to send epsilon to 0. So it turns out that also geometric tensor or fidelity susceptibility is related to this object. You all know about Berry curvature, and it turns out it's just average of anti-commutator of A alpha and A beta. So a generator of adiabatic transformation induces all this geometry we know, quantum geometry. By the way, its expectation value is Berry connection. So you all heard about it, I think. But probably you heard less, or maybe some of you heard, about so-called fidelity susceptibility, or more generally a quantum geometric tensor, which is nothing but overlap of derivatives of the wave function if I do my small change. So it basically tells us how fast my eigenstate changes if I do infinitesimal perturbation, right? And then you just do overlap. And if wave function doesn't change much, it's a constant. If it changes fast, it's a big number. And then because my gauge potential is basically derivative operator up to whatever h bars, this is just metric tensor is a covariance of this adiabatic gauge potential. So this object, which tells us about adiabatic transformations, it also tells us about geometry. It also tells us about conserved quantities. So it's extremely rich object. And by the way, this is not studied well, but if your lambda is time, then generator of time transformations is Hamiltonian. And then you can think about variance of the Hamiltonian as a measure of distance in time. And this sort of makes sense if you start from exact eigenstate of the Hamiltonian. This is 0, and this is 0. And of course, nothing happens. You have stationary state. Your wave function doesn't change in time. But if you start from superposition of the states, your wave function starts changing in time. And variance of the Hamiltonian tells you about this. Anyway, so many interesting connections with many things. So now, one thing, this is already like our work, which I want to maybe advertise a bit without going to details, and maybe I'll show the slide which you saw from Marco's talk, I'm not sure. So we can use this fidelity, susceptibility, or sensitivity of eigenstates maybe as a probe of chaos, with the idea that if the system is chaotic, our eigenstate should be extremely sensitive to small perturbations. And if it's not chaotic, it should be less sensitive. And then I also, this is a plot sort of which was generated by Brice. I don't want to go into sort of all the details, but what I want to highlight is that I just emphasized also that this probe is sensitive to long time dynamics, and it can be very sensitive to exponentially small perturbations because it feels like exponentially long times. This epsilon, which I mentioned before, is basically a time cutoff. So this is, let's basically make formulations. So this is this adiabatic gauge potential. This is its norm, which is, as I explained, fidelity susceptibility or metric tensor. And then you heard already from Marcus that if you have ergodic ETH systems, then matrix elements between eigenstates scale as e to the minus entropy over 2. So I'm assuming he explained where it comes from, so I don't go into the details. S is entropy of the system, right? So in big systems, it's extensive. So matrix elements are very, very small. But energy denominators or energy differences between nearby states are also very small. Like distance between nearby energy states is e to the minus s, 1 over density of states. So if you just take one term in the sum, say nearest neighbors, then numerator is e to the minus s, the thing squared, denominator is e to the minus 2s, and we get that susceptibility is e power s. So, and this is exactly what I was trying to say. In chaotic systems, we have exponential sensitivity of eigenstates. So entropy is extensive in system size. It doesn't have to be 1D, it could be system volume, but let me just focus to 1D just to be specific. And then we see that we have really exponentially tiny perturbation basically creates already orthogonal states. That's what chaos is. And it actually reminds probably a lot like classical chaos, that I have sort of analog of Lyapunov exponent, but instead of time, I have space. So anyway, in both cases, I have exponential sensitivity. Well, if we have free systems, then this adiabatic gauge potential is just local extensive operator. Extensive, we have extensive perturbations, basically well-defined, sort of like angular momentum or momentum. So it's a nice operator, and its norm is polynomial. And then if we have more complicated integrable systems, we're not sure what to expect, but at the end from numerics, and then we develop some understanding. So this fidelity stability is also polynomial in the system size, but with sort of larger exponent than free models. So basically, the short story is that it is this fidelity susceptibility or norm of this gauge potential seems to be like a very good probe of quantum chaos, or just not necessarily quantum, classical as well. So in classical, this just diverges because this C will diverge with H bar. So, and this, I don't know if Marcus showed exactly this slide or not, but even if he did, I think it will be a good reminder. So this is some numerical result, which was done mostly by Tyler LeBlanc, who graduated now from Penn State. And then we just decided to test like what happens numerically. If you take a model, this is just a spin chain, and I'm sure Marcus mentioned like many chains like this. And it turns out that, well, it has some spin flip terms, it has some interactions nearest neighbor. And without this term, this model is known to be integrable. It can be solved by Bethe ansatz. It's a complicated solution, but you can write an analytic solution. You can find all eigenstates. And once you add this term, which is say second nearest neighbor interaction, then integrability is lost. And then we were interested, can you detect using this fidelity susceptibility how quickly system becomes chaotic? So we look in the probe into the sky, and then instead of averaging over eigenstates of this object, we average log of this quantity of eigenstates. This is needed for technical reasons, but this is really not important, so I don't want to emphasize it. In the first paper with Mihit, we just introduced small cutoff. Anyway, this is just to regularize things a little bit. And then we look into different observables. These are my d lambda h, which is either nearest neighbor interaction or second nearest neighbor and so on. And then we found like interesting, very interesting results, which show that indeed probing quantum chaos in this way is very useful. So what's plotted is this fidelity susceptibility, which is appropriately scaled. So it's basically fidelity susceptibility times e to the minus s. We were a little bit more careful. Don't want to explain really these numbers, but just to minimize finite size effects, sometimes it's really important how you scale. Anyway, so if it scales exponentially with system size, then after this rescaling, it should be a system size independent constant. And then we see horizontal axis is delta prime. Let's focus just on top figure. So we see that everything collapses to the same curve. So this is ETH. This is exponential scaling. But then if we look carefully at even smaller integrability breaking perturbations, we see that this fidelity susceptibility is huge. So it's super sensitive. And it turns out it scales as e power 2s. So just to make long story short, so what seems to be very generic picture of how chaos emerges in interacting systems is through like extremely interesting and not well understood phase. So if some of you are like interested in doing research, I think this regime is very, very interesting, very poorly understood. So roughly, this is like a cartoon, but I think it worked in all the examples we analyzed. So we have vertical axis, which is integrability breaking in log scale. So here it means it's exponentially tiny. Here it's already of the order of 1. And here we have a system size. And then, of course, if perturbation is so tiny, your system is roughly integrable. So color means basically scale for fidelity susceptibility. If your perturbation is big, then you see like ETH regime. But in between, you have this extremely strange regime where ETH doesn't apply. So you're not ergodic, you won't get thermalization and so on. But you are super sensitive. You are more sensitive than ETH. So you have, in some sense, maximal chaos. So in thermodynamic limit, both this line and this line go down. So if you system size in infinity, eventually you will go to ETH regime, but you will probably see some leftovers of this. Okay. Now let me go back to counter-adiabatic driving. So I introduced it. So we have a moving Hamiltonian, and then my CD Hamiltonian will have this extra Galilean term, which I add to it. So what I just mentioned, that in generic ergodic systems, norm of this operator, which is again another way to define fidelity susceptibility, is exponential in entropy. So it's exponential in system size. So it means that it's just hopeless to generate such exact protocol. And this is, by the way, a sort of more refined way to see Yerzynsky result of 95, why in classical systems, chaotic systems, it doesn't exist, because this entropy, it contains log of h bar. When h bar goes to 0, it diverges. So it's either in classical limit or thermodynamic limit, this quantity becomes infinite. So we can only do something approximate, but let's just see how it works if we do approximate driving. And by the way, from what I just told you, there is a general statement that if we have integrable systems, then this CD driving is polynomially easy. So it means that if you just build a quantum computer or quantum device consisting from integrable circuits, then it's not exponentially hard problem. Okay, so coming back to chaotic systems. So I just said that we need to minimize square of this object, right? So we try to find some good approximation for A, which minimizes norm of this guy. And we hope that our protocol will work. So this is sort of the last maybe technical slide, and then I'll show examples. So how do we find good variational ansatz? Well, this is again an exact expression which I showed to you. So we have d lambda h in Heisenberg representation, and we have to integrate it. And then we realize we can do expansion commutators. So if you write what this T lambda H is in the Heisenberg representation, do short time expansion, that's what you'll get. So we'll get T times commutator plus, T cubed times third of the commutator, and so on. So this is basically Baker, Campbell, Hausdorff formula, one version of it. And then we can explicitly integrate, and then we get this expression, and it's clear that when epsilon goes to 0, it's sort of ill-defined. So it's a very badly convergent expansion. However, we can say, well, let's just use this as inspiration. And this was idea of Peter. Let's just use this as variational ansatz. So we basically say that we will look for our adiabatic gauge potential in the form of these commutators which appear in this expansion. So again, d lambda h is what we are changing, h is our Hamiltonian. So, and then we get only odd terms. And again, in classical, it's exactly the same story, but we have Poisson brackets. So classically, the problem is not easier, but we can write exactly the same. And then we find these coefficients variationally. I don't really have time to explain how variational procedure works. But let me just say, this is simple. Simple in the sense that you don't need to diagnose Hamiltonian, you can take thermodynamic limit and so on. Of course, complexity comes when you add more and more commutators, it becomes harder and harder, but at least system size and so on, it's not really a problem. So let me consider now an example. So this was done by actually undergraduate student in BU, Nick. So let's just take first just a single nonlinear oscillator. And suppose we want to turn on nonlinearity. And then we want to do it such that we don't excite our particles, say, from quantum eigenstates or from microcanonical ensembles. Again, quantum and classical formulations of the problem are very similar. It's kind of clear why we get non-adiabatic effect if we do it quickly. Because if the particle is in the middle, it doesn't even feel that we added some potential. Its energy remains the same. But if particle is on the edge, we suddenly increase its energy by a lot, right? Because our potential energy goes from x squared to x squared plus x power 4. So if we do it quickly, we will create lots of fluctuations in the systems. So on the other hand, if we do it very, very slowly, all particles are the same. They move back and forth, and they sort of on average experience exactly the same potential. So if we raise slowly, our potential will remain microcanonical. So, and indeed, so if we don't do counter-diabatic, we just look into energy variance as a function of duration of the protocol, that's exactly what we find what we expect. If protocol is very slow, we have very small energy variance. But then if protocol becomes fast, we get like large energy variance. So we are non-adiabatic.
Excuse me?
Yeah.
There's another question. Regarding the diagram with integrability and maximal chaos, is it possible to put many body localization phase somewhere on that diagram?
Yeah, I didn't talk about it. By now, we concluded that many body localization is exactly the same in a sense that there is no many body localized phase in thermodynamic limit. This was a mistake. There are still debates about it, but at least with Dries, we are kind of convinced. But yes, so you will see exactly the same story. I unfortunately didn't include the plot, but it will look exactly the same. So essentially, if you think about integrability breaking as a hopping, then if you have just a zero hopping or the same as infinite disorder, you will be here. Then you go through this maximal chaos phase, which I think everyone missed. And this actually the phase which creates a lot of problems. It makes all renormalization group analysis of MBL unstable. And then eventually you go to ETH regime. So there are some caveats. So some of these lines are not exponential, but polynomial. But again, this is not related to disorder, but something else. So if we have time, I'm happy to chat a bit more about this after the lecture, or just reach me privately, because it will take me time to give a long answer to this question. But essentially, it's the same. We don't see any difference. So I don't know, maybe Marcus also mentioned some numerical results which show that for Anderson insulators, there is really no difference between disorder and non-disorder. Okay, so I'm back to this much simpler problems potential. And then we ask, what is CD driving? And then what I'm doing, I'm just basically generating, or it's actually Nick is generating these commutators. So d lambda h is in our case nonlinearity, which we change in time, so x power 4, and h is our Hamiltonian. And then we compute these Poisson brackets. It's not that difficult. And what you find that in the leading order in that expansion, you get term which is px cubed, and in the next leading order, you also get xp cubed. This is a very unusual term. And then we just see how we are doing. So we turn on nonlinearity. Again, this is the same time scale. This is the curve which I showed you just before. And then we add leading order counter-diabatic term and a next order counter-diabatic term, where these coefficients found variation. And then I just see, well, leading order already gives you some improvement, but if you go to next order, so if you can realize xpq term, you get like amazing improvement. You get like, I don't know how many orders, like 3 orders of magnitude. So you really get a lot. One can ask, oh, maybe the problem is very simple, but then actually Nick checked the full Fermi-Pasta-Ulam single FPUT chain. For those who know, it's the classic example which gave birth to basically understanding classical chaos in many particle systems. Anyway, this problem was studied to death, and it's still there are many actual questions. Anyway, so by now it's believed to be non-integrable system in thermodynamic limit. Anyway, so we repeat the same thing. Our Hamiltonian gets more complicated. It involves like still powers of p cube and x, but now there are different, well, x q's, some differences of q's, like basically discrete derivatives and so on. It looks complicated, but it's polynomial of third power, and it involves only second and nearest, first and second nearest neighbor coordinates and momentum. Anyway, so you get this crazy term, and you try to do the same numerics, and you again find that somehow it's almost like a magic. It works, right? So we turn on this extra counter-diabatic term, and then we create very tiny energy variance. It's not really as good, but it's almost as good. You might see we get really 2 orders of magnitude, and this is already thermodynamic limit. So it's not that when you go to 500, things will change. So they will be the same. I mean, of course, we define energy variance by n just to have intensive quantity and so on. So there is a question of implementation. I see that I'm kind of running out of time, so let me skip this example, show another example, which is sort of application to quantum annealing, and it comes not even from our work, it's work of Andreas Hartmann and Wolfgang Lerner from Innsbruck. So they took some complicated Hamiltonian, so this is a model which was actually proposed by Wolfgang himself, Philip Hauke, and Peter Zoller, to do some adiabatic quantum computing. So you can just, it's complete, so you can encode anything there, and they wrote some 4-spin interaction to realize it on some, I don't know, D-wave machine or related computers and so on. Anyway, this is not what's concerning me. But what they want in quantum computation is to do adiabatic process, right? To stay on the ground state, you start from strong magnetic field, and then at the end of a protocol, you only have these guys, and then you want to find ground state of this Hamiltonian, which encodes some complicated problem. And they said, well, let's try to do leading order counter-diabatic. And it turns out in the leading order, one commutator, you get only spins sigma y. So, and you know how to drive them. Again, this is variational solution. I'm not going into detail. They used exactly the same variational method. And then again, they can find this in thermodynamic limit. So they don't need to diagonalize anything, whatever. They just need to know coupling. And then they looked into the different measures. One is energy above the ground state after the end of the protocol. Another is fidelity. So how close their state to desired state. Of course, it's a small system size. And then they find again very good improvement, even from first order counter adiabatic. So they see like fidelity is again function of time. So this is fast, this is slow. They see if they are fast. If they do nothing, they get basically zero fidelity. But if they do slow, they get like considerable improvement in fidelity. And same as energy, it's opposite. So you see very little energy. It's kind of interesting to have this minimum, and yeah, I won't have time to discuss it, but it's still an open problem logic. So it turns out that there were many similar results by other groups. So the only issue is that, which I didn't discuss yet, is how we do with terms like XP cube. So in this example, this will be like 3 spin terms and so on. How do we implement them in the lab? And so this is the last piece I want to mention in, I guess, last 5 minutes. So it's something which also Peter realized first, that it turns out that this commutator expansion I showed you is extremely convenient because we can also realize it in the lab using Floquet. Periodic driving. So I won't have time like to discuss this in detail, but let me just say the answer. So we discussed that a general form of AGP and good variational ansatz is this odd commutator expansion. And it turns out that if we shake the Hamiltonian, where say we shake H and d lambda H at some high frequency, and then we want to try find what is the Floquet Hamiltonian in the high frequency expansion. So for those who know, we get expansion in commutators, which are very similar to these ones. For those who don't know, you have to trust me on this. So Floquet Hamiltonian is like in Kapitsa pendulum. It's effective Hamiltonian, which drives slow dynamics if you average over fast motion. So now the task is how we find the drive where we get only needed terms. Usually in Floquet, we get all sorts of commutators where H and d lambda H alternate in arbitrary order. And it turns out like Peter found some constructive way which shows that this is possible. So it means that in the lab, and this is a general statement, if you have control only of d lambda H of what you change and your original Hamiltonian, then you can just realize this dissipationless protocol. You don't need any extra control of parameters. So maybe I'll show just one example because I think I'm running out of time. So this was experiment which was done at BU in Alex Sushkov lab, which is just a single spin which we try to flip. It's a very simple problem. So we're trying to flip spin 1/2 from up to down. So essentially, it's also a Landau-Zener problem. So we have some magnetic field along Z and magnetic field along X, which we change them from large positive value to large negative value. So in the end, we kind of rotating it. Then I already said in rotating frame, we basically get our counter adiabatic Hamiltonian, we get extra sigma y times angular velocity. So this is a complicated way to write angular velocity. Then we can do something like a waiter. So in this case, it's possible we can do this unitary rotation, which is identity in the beginning and the end. And then we can get fast forward Hamiltonian, which only involves Z and X magnetic fields, which depend on time in some complicated but known way. And finally, we can do Floquet engineering. So where we also basically realize this Hamiltonian, but now we shake sigma Z and sigma X. And of course, I don't have time to explain these dependencies. Yeah, and the long story short, it works. So, and in some sense, here's a comparison of fast forward and Floquet. They're kind of equivalent and they expected. So this is now time within protocol. It's not duration. And then you find that in the beginning, and then you measure fidelity. So you start from 0 fidelity, you start in orthogonal state. And at the end of protocol, you start with a very good fidelity close to 1. So it works. But then we also realized that Floquet protocol is much more robust against noise. It's probably a technical detail, but anyway, this I want to mention. I don't think I have time for this, so let me just summarize. So what I told you is that one can construct efficient local counter-adiabatic protocols in many particle systems. And we have like many, many more examples. I showed few, but of course, this looks like a very powerful method in general. So, and moreover, one can realize them in a lab with no additional controls required. We can do efficient state preparation and significant improvements in fidelity and so on. Of course, I'm not saying that we can solve NP hard problems. So it still has to be studied how big improvement we get. But at least in conventional problems, when we don't go to these glassy phases or whatever, improvements is significant. Then I told you about sort of another part that we can define and analyze quantum chaos through AGP. And I think now we are trying to understand chaos in classical systems, how we can connect these things. So this adiabatic gauge potential is defined through non-equal time response, which is defined classically, but it also tells us about how eigenstates change. So hopefully we can connect Lyapunov exponents and random matrix theory, but we'll see. And then I didn't tell you about any other applications. So we can use this machinery to identify dark states, or sometimes people call them like quantum scars, do Schiffer-Wolf transformations. This is something not done, but it seems that you can regularize divergence of field series. You can find new integrable systems. You just find this quasi-local adiabatic gauge potentials and generate them. I also didn't tell you about quantum speed limits, but this object also shows up. Then building like optimal local Floquet Hamiltonian is also like seems to based on this. And I put many dots. There are many, I think, possible extensions of this machinery. Okay, well, thank you very much for your time.
Thank you so much, Professor, for the talk. If anyone has any questions, then now is the time for them. I see there is a plea already for, could you please elaborate on the relation between AGP and the integrals of motion as introduced by Mierzejewski et al.?
Yes, so so let me just go there, right? So yeah, this was not obvious, I have to say. So it's not that it just sort of immediately, this relation immediately follows. So I told you that basically finding AGP is equivalent of finding this G, which commutes with Hamiltonian. And what is G? It's essentially our perturbation, which we're adding to the system, like conjugate to lambda, right? So again, if lambda is electric field, this will be a dipole moment. If it's magnetic field, this is magnetization in the system. And then we are trying to do also local unitary rotation to make this thing diagonal with H. So we're basically trying to remove off diagonal part by rotating the basis. And then we are finding an object which commutes with the Hamiltonian. So this is, if you want, dressed perturbation, infinitesimally dressed, everything is infinitesimal here, right? So this dressed perturbation is an integral of motion because it commutes with Hamiltonian, right? But then what came out from just mathematics, algebra, I really don't have at the moment explanation, like hand-waving explanation why this works. Then this object is equivalent to time average of my operator d lambda h at fixed Hamiltonian, but in the Heisenberg representation. So if you want, if again, lambda is magnetic field, I look into magnetization in the Heisenberg representation when all the parameters are fixed, nothing depends on time, right? And then generally this object doesn't commute with H. Well, if it commutes with H, d lambda h of t is constant, and this integral gives me 1, so I go back to what I can. But generally it doesn't commute. But then this was idea by Marcin and others, is that Well, if we just do time averaging of this object, we average all of diagonal elements to 0, and the remaining part will be the part which commutes with the Hamiltonian because it's diagonal, right? So if you write d lambda h of t like matrix elements, they will be whatever e to the I en minus emt, right? So all matrix elements which are of diagonal will average to 0. And this will be like your diagonal operator. So it's integral of motion. And they basically said, well, let's just, for lambdas, we will try all possible, or for this operator, the lambda h, all possible local operators. And then we can count all possible integrals of motion. Usually in ergodic systems, this operator becomes super non-local after time averaging, and basically doesn't contain any new information. So it's not a local operator. It's like a projection operator to eigenstates. But in integrable systems, there is some leftover. And it turns out that this leftover is exactly what we are finding here. So if you find approximate gauge potential or regularized this gauge potential and find this object, then it's the same as if we do time average of this. I don't know if it answers the question or not, but this is.
I think, yeah, it was thorough. And there is a follow-up. Is this integral of motion local, quasi-local, or rather non-local?
Well, that's a good question. In that paper, actually, they found quasi-local integrals of motion in this way. And then I think they realized later how to get them from, Petty ansatz, from like this integrability machinery. You find all integrals of motion like that, essentially. I don't know if there is a mathematical theorem which tells you that if you try all local operators and daytime average, you will list all integrals of motion, but at least it's very logical that this has to be the case. So, and in this sense, it's consistent with what we are saying. So this A lambda in integrable systems is not a local operator generally, but it's quasi-local operator. And this is reflected in the scaling I mentioned. So we found it only numerically. Let me just do it quicker. So we found the scaling only numerically, so I wouldn't say we really understand it. Yeah, it's here. But essentially, if A would be a local operator, so if you get local integrals of motion, then you can show that extensive systems always get this scaling linear, right? Because variance of a local operator, if you want, is extensive. This is central limit theorem. But what we found that you get high order powers. So like we found in XXZ model, k equals to 2. So it means that this A lambda has to have some tails. It's quasi-local, but it's still not non-local like in ETH systems where this norm is exponential. So this still means local in Hilbert space, but it's not local in ordinary space. So we don't really know what it means.
Okay, so thank you. I think there's a last question. Can we, and how to apply this theory to find new integrable systems?
Well, this is actually, I think, a very good direction to try, because now you can just find arbitrary A lambda, which is say quasi-local, which is non-trivial. I think if you find this gauge potential, which is local, you will probably recover what people already recovered. But what you can do, what is possible to do, I think, is to really find some quasi-local operators, non-trivial operators, and then basically use them to generate unitary transformations, and then if you want dress Hamiltonian with them, and then you'll get families of integrable Hamiltonians. So what we seem to learn, which again, I'm not expert in integrability, but when I talk to experts, they say this is sort of partially known, but not formulated in this way. So what we see that in all integrable models are actually families of integrable models, and you can move with this adiabatic gauge potential between these families. So if you start from some quasi-local operator, and then you can generate new integrable models.
Okay, thank you.
How will it be different? Can you really find something genuinely new, what people really don't know yet? I just don't know. I don't feel like I'm expert in that field. But I think it's interesting to try.
Okay, I think that's all. Then thank you again for the talk, Professor, and thanks to all the participants. Now, if you just give us a few minutes, our leader of committee will say a few final words to close the conference. And thank you again for coming.
Well, thank you, everyone.
Hello, can you hear me? Okay, and can you see me? Oh, it's new. Okay, so I think we can begin the end of our conference. So hello, everyone. My name is Damian Ziomko, and I was the chairman of organizing committee of this conference. I'm very happy that we could spend the last 5 days together, despite the fact that many of us were even thousands of kilometers away. I hope that conference was an interesting experience for you. The lectures and workshops allow you to learn a lot of new things and that they are satisfied with your presentations. All information regarding to the confirmation of participation and prizes will be sent to your email soon. So at the end, I would like to thank our great jury for great job with presentation and posters, O'Reilly for access to interesting books for our participants, our partners, SoftServe for their support both financially and substantially with a truly fascinating lecture, Polish Physics Society for honorary patronage, Wrocław University of Science and Technology, and especially the Faculty of Fundamental Problem of Technology for inspiration for create this conference. Our wonderful guests, who despite different time zones and hard work to development of science, found time to introduce us to the arcana of their research areas. And of course, thank to you all who actively and passively participated in our conference. I hope that we have managed to meet your expectations and that we will see you again next year. Lots of success and good luck. Thank you very much for being with us.